Yes, sir, you are audible. Please go ahead.
Okay, okay. Thank you, madam, for this nice introduction. So, first of all, I would like to congratulate the whole EICT team for organizing this wonderful course at right time and also giving me this opportunity to share my views. So, I guess this is the right course at the right time because of this Government of India initiatives. So I wish all the participants very best and I guess we can quickly start. So let me share my screen. Is my screen visible?
Yes, sir. Yes, sir.
Okay, okay. So we can quickly. So today I will be sharing. So I guess my camera is not needed for the bandwidth purpose. I guess I can shut my camera off.
Yeah, you can do, sir. No problem.
Okay. So today, the topics which I would like to discuss will be, I'll be discussing that DC biasing in the MOSFETs, the small signal analysis, and the MOSFET amplifiers. So first of all, let's discuss like what is the need of biasing? Why do we bias the transistors? So all of us know that MOSFETs, they are active devices. And the meaning of active device is like the device first of all needs to be turned on in order to demonstrate its real performance. Say for example, we know like R, L and C. These are the example of passive devices. Like we need not to turn these devices separately on in order to show either the resistive, capacitive or inductive behavior. So as soon as they are connected in the circuit, so they display their normal behavior. But as far as the active devices are concerned, for example, like the transistors, so they need to be first turned on in order to operate their transistor behavior. So that is the basic reason like why do we bias the transistors. So now, how many different, now if I talk literally, like what is the meaning of biasing? That was the reason of biasing. And now what is the meaning of biasing? Biasing is basically what you call, it is an arrangement of external circuit components like the resistors, the capacitors and the voltage supplies around the transistor so that the transistor can be operated in the region of interest. Like all of us know, like maybe in the previous classes you might have studied like the main region of operation of the MOSFET, it is like cutoff, linear and saturation. Now, depending on the values of your R, the resistors and the voltage supply, its region of operation, it can be changed. So now how many different type of biasing arrangements are there? So though there can be n number of biasing arrangement, but there are some standard biasing networks that we generally follow. So I'm going to discuss those biasing arrangements. So the first one of them is fixed bias, then it is self bias, voltage divider bias and common gate. So let's take one by one each one of them. Yes, and also this biasing, it also depends on like the type of MOSFETs. So in the previous class, you might have studied like there are two types of MOSFET, like the depletion and the enhancement. So since the current equation in both types of MOSFETs, those are different, right? In the depletion MOSFET, we have this Shockley's equation, like this ID is equal to IDSS 1 minus VGS by VP whole square. So this is the Shockley's equation. Whereas in the enhancement MOSFETs, we have the standard FET equation, like in the linear and the saturation mode. Since these two current equations are different, so that's why the biasing will also vary. Like the nature of the biasing, that will also vary. And apart from this, it is also essential for us to understand few rules of the DC analysis. First one of them and the most important is that wherever capacitor is present, because generally when we make the amplifier circuit, so generally we put like the capacitors at the input and the output port to block the passage of the DC current in the either the input side or the output side. We have to put some like the bypass or the coupling capacitors. So those type of capacitors we have to put as the open circuit whenever we are doing the DC analysis of the biasing network. So let's take first the case of a fixed bias network in the depletion MOSFET. I guess I need to write. So let me come out of this mode. Yes. So I guess this fixed bias circuit, it is quite a simple network. So where you connect one resistor with the drain terminal and the one resistor with the gate terminal, and you supply a negative voltage at the gate. Now this discussion here, it will be mainly focused around the N-channel MOSFETs, depletion MOSFETs. So now let's try to write the biasing equations. So here we know that in the gate terminal there is no current for the MOSFETs. The reason being there is oxide. Though this leakage currents will be present, but as far as circuit analysis is concerned, we have to ignore the leakage currents, and we will assume that no current flows in the gate terminal. So if I write the this biasing equation, or let's say the KVL equation more precisely, in the input loop, in this loop if I write the KVL equation, so what will be that? So if I start from here, ground, so what will be that? It will be plus VGG, it will be plus VGG plus IGRG. Since the gate current will be 0, I am not writing that current, okay? So plus VGG, that will equal to your VG plus VG. Okay. So you can see here VGG plus VG is equal to 0. And so what will be VG from here? VG is equal to minus VGG. And now we have to plot this equation, the VG equal to minus VGG at the transfer characteristics of the depletion MOS. So you might be knowing that this is the transfer characteristics of the depletion MOS. So this is also visible here. So ID versus VGS. So this light blue characteristics, it represents the transfer curve of the depletion MOSFET, whereas this black straight line, it represents the VG equal to minus VGG line. And wherever these two curves intersect, so that determines the point of your MOSFET. So we will also learn by the example like how we can actually find the operating point in the real circuit. So first of all, let's analyze few of the practical networks. Next biasing arrangement is your self bias. In self bias, no external bias is applied except VDD. So in the RG side also there is no bias, no power supply, only power supply present in the circuit will be VDD. So what is our task? We first of all have to find out like what is VGS in this circuit. So if I write VGS, so what is VG here? VGS will be what? VG minus VS. So VG here is what? 0. Why 0? Because we know that no gate current passes from the terminal, gate terminal. So that's why IGRG drop will be 0. Then what is, so 0 minus Vs. What is Vs? Vs will be IDRS. And now from where ID is coming? ID is coming from the top, from drain to source. Since we know that drain and the source current will be equal, so that's why I am denoting that current with ID. So what will be that? It will be IDRS. So what will be the equation of VGS? VGS will be equal to minus IDRS. Now if you notice this equation, this is something, this is the equation of a straight line, like y is equal to mx plus c. Here c, of course, it is 0, the intercept is 0. So y-axis, now where is the y-axis? Y-axis is your ID axis and x-axis, that is your VGS axis. So ID versus VGS, again in this graph you can see here that this light blue curve, it represents the transfer characteristics of the depletion MOSFET, whereas this black straight line, it represents the equation of the load line, so which is VGS equal to minus IDRS. Okay, you can also notice that this equation of the load line or this straight line, it is passing through origin because we do not have any intercept here. Intercept is 0. That's why this load line, it is passing through this origin. And wherever this transfer curve and the load line intersect, that becomes your Q point or the operating point. So let's move to the next arrangement, that is the voltage divider bias. In voltage divider bias, you can see the arrangement again is quite simple. It is not that much complicated. So again, our first task will be to write down the equation of the load line, or we can say like what is the VGS here. We have to write down the equation of VGS. So VGS will be VGS equal to what is VG here? VG, again we know that no current passes through the gate terminal, so that's why whatever is the voltage across R2, that will be the voltage across gate. So this VG we can write as the voltage divider of VDD on R2. So this I can write as like R2 upon R1 plus R2 into VDD. Okay, so that becomes my VG minus VS. What is VS here? It is again ID RS. Okay, so this equation is the equation of the load line, and now this equation of the load line I need to plot on the along with the transfer characteristics of the depletion mass. So here again in this diagram, this this light blue color curve, it represents the transfer curve, whereas this line, this straight line, black line, it represents the load line. Now, how to plot this line? We can find out the x and the y intercepts. So equation of the load line was this. Now if I have to find out the x intercept, so I need to put the y equal to 0. So if I put y equal to 0, let's say if I put this term equal to 0, so what will be equal to VGS? VGS will be equal to this R2 by R1 plus R2 into VDD. So that will be plus VG term here. Okay, this intercept. Okay, it will be R2 upon R1 plus R2 into VDD, whereas the y intercept, this point, this will be what? To find out this intercept, we have to put x intercept to 0, that is x equal to 0, like VGS we have to put to 0. So if we put VGS equal to 0, so what will be the value of this current? It will be equal to this divided by Rs. So this will become the ID. So again, wherever this straight line, it will intersect with the transfer curve, so it will determine the operating point. And one interesting point here is that how can you change the operating point, like the region of operation? Maybe in today's class or maybe a few classes before, you might have studied that there are two regions of operation of a depletion MOSFET. One is the depletion mode, where like from 0 to VPP, and another mode is known as enhancement mode, which operates in the opposite side of the VP, right? So if we have to change the operating mode, so how this operating mode can be changed? Just by changing intersection point. If the intersection point lies in the depletion side, so it will be operating in the depletion region, and if the intersection point, if it lies in the enhancement side, so it will be operating in the enhancement region. So one example I can show, like the complete characteristics of the depletion MOSFET is something like this. If the slope of the load line, basically the slope of the load line, that is also determined by the value of resistive components only. Okay, if we adjust our resistive component such that slope of the line is something like this. Okay, so here you notice that this intersection point, it is lying in the depletion region. So that's why here in the depletion mode side, so here the operating point, it will lie in the depletion region. Whereas if I change the resistive component value such that slope of the line increases, say that it can also, we can have a load line like where is the intersection lies in the enhancement mode. So in this way we can change the operating region as per our choice. If we have to operate the depletion MOSFET in the depletion region, then we have to adjust the component value such that the slope of the load line is less and the intersection takes place in the depletion region. And if we want the depletion MOSFET to get operated in the enhancement side, so we have to adjust the component value such that the slope of line is more and the intersection takes place in the enhancement region. So let's see one or two more examples of the biasing networks. So the network, whatever is seen here, that is the example of a common gate biasing network. Here also, see, our basic task to determine the operating point, it will remain the same. Like wherever we have to find the operating point, we have to find out like what is the VGS. Okay, so if I notice what is the VGS here, so let us try to write the KVL. The VGS here, VG is what? 0. Since the gate it is at ground potential, so VG is 0 minus Vs. Now what is Vs? Vs will be ID Rs minus VGG. It is sorry minus, okay. So again, if we notice here in the transfer curve, so ID versus VGS. So this black line, it will be the equation of the load line, and again wherever it will be intersecting with the transfer curve, that will determine your operating point. So let's try to solve one example, real example with the real circuit problems. So let's say if we have to determine the operating point for this particular biasing arrangement. So how will we proceed? So we are given some information that this is a depletion MOSFET having IDSS as 6 milliampere and VP as -3. So let's try to solve this problem. Okay, let's make the transfer curve. So IDSS, it is 6 and this is -3. Okay, let's try to solve this. We have to find out the VGS because since this is depletion MOSFET, so the drain current equation will be given by the Shockley's expression, which is ID equal to IDSS. IDSS is what? It is 6, 1 minus VGS by VP. Now VP, make sure that it has to be written with proper polarity. So ID is equal to 6 IDSS 1 minus VGS by VP whole square. Okay, now the second task will be to write down the equation of the load line. Now what is the equation of the load line? So we have to find out VGS. VGS is equal to VG. VG is what? VG is the potential divider of 18 volt on 10 and 110 mega ohm. So if I write it, so it will be 10 divided by 120 into 18. That will be my VG. Okay, and I guess this comes out to be maybe 1.5. Okay, I'll rewrite it later in the simplified form. So it was the VG term. Now what is RS? RS is 750 ohm. So I will write that as 0.75 ID. Okay, so let me write this in the simplified form. VGS is equal to 1.5 minus 0.75 ID. It is 0.75 ID. Okay, now we have this equation number 1 and this as the equation number 2. Now we have to solve these two equations parallelly. What we can do? We can put the value of VGS from 2 in 1. So this will be equal to like I'm writing this ID is equal to 6, 1 minus VGS. VGS is what? It is 1.5 minus 0.75 ID divided by minus 3, then whole square. So if you will open this square and rearrange, this will become a quadratic equation. So quadratic equation, so we have to find out roots. So I'm writing down this equation, like I have solved this in advance. So I hope this basic calculation can be done by everyone. So let me write its roots. Let's try to find out its root. So the equation was the simplified equation will be point 377 ID square minus 5.52 ID plus 13.56 is equal to 0. 0.37 ID square minus 5.52 ID plus 13.56 is equal to 0. Now we can try to find out its root by applying the roots formula. So what is that? That is minus b plus minus b square minus 4ac under root divided by 2a. So if we do that, so what will we get? So I am simply writing down the value of the roots. So two roots which we will get after solving this equation, it will be 11.51 and 3.12 milliampere. Okay, now these are the two possible values or the two possible solution of this quadratic equation. Now the question arises that which of the values to be selected. Now in order to select a proper value, we have to check the transfer curve and the load line equation. So we can draw this. So this was the transfer curve. IDSS was 6 and VP was minus 3, and the load line equation was 1.5 minus 0.75 ID. So here the intersection, it will be the load line equation was something like this. So this point was 1.5, okay. The intersection is taking place somewhere here, okay. So this value has to lie between 2 and 6, means whatever is the solution of this equation, that has to lie between 2 and 6. And what is that value? It is 3.12. So the possible solution is here, or the possible solution here is 3.12. 0.12 milliampere. Okay, and once we get the value of ID, we can use either the Shockley's equation or the load line to get the value of VGS. So this is one example of voltage divider. So let's try to solve another example, which is of self-biasing network. So let's try to first of all write the equation of the load line. The equation of the load line will be what? VGS is equal to, VG is what? 0, because of no current flowing from the gate terminal, and VG minus VS. What is VS? VS is 2.4 times ID. Okay, so what is the VGS? Effectively it is minus 2.4 ID. Now we have to substitute this VGS in the Shockley's equation, that is the device equation. It was ID is equal to IDSS. What is IDSS for the given device? IDSS 1 minus VGS. I am directly writing VGS as minus 2.4 ID upon VP. VP with sign is minus 8 square. Okay, this again is a quadratic equation. If you will open this quadratic equation, so the simplified equation that I have solved in advance, so I am writing that. So this will become, so maybe simultaneously all those who are following this, so they can also try to find out the simplified equation and the roots of that equation, so that we can verify. It is 5.76 ID square minus 46 point ID plus 64 is equal to 0. So here I'll be taking the break for maybe some few seconds, so that all you can also reach on the same equation. So then we will continue.
Sir, we are not able to hear your voice.
Madam, I'm taking a break for maybe 20 seconds, so that students or those who are following, so they are able to get this equation. They are trying to solve if they are following.
Okay, sir.
So I hope few of you might have reached on this equation. So this is the quadratic equation, and we can find out the root by the standard uh, application of the formula, root formula, that is minus b plus minus under root of t square minus 4ac upon 2a. So using that, so the roots which have been found are 6.29 and 1.76. Okay, so now these are the two solutions. Now which one of them to be selected? So to make a decision, we will follow the transfer curve and the load line. So here this is what So that will be the equation or the straight line passing through the origin like this. And here we can see that the intersection it is occurring here. Okay, and this value it has to lie, or you can say, in the lower half, which is less than 4. Less than 4, any value less than 4 in the solution, two solutions we have obtained, that is 1.76. So 1.76 milliampere is the solution for this biasing network. Here means ID is 1.76 and the ID is 1.776. Then what will be the VGS? We have this equation, VGS equal to minus 2.4 ID. So what will be the VGS? VGS will be equal to minus 2.4 times 1.76. So this will become the VGS. So in this way we can determine the operating point. So one thing which you can compare from the BJTs, like in the BJTs, the operating point, it is the set of like IC and the VCE value. Okay, and the IC VC, the set of IC VC you can get from the output characteristics of a, let's say, common emitter BJT. But here in the case of MOSFETs, so you have to find out this on the transfer curve, that is the ID VGS curve. There in the case of BJT, it was the output characteristics. Here in the case of only difference which we have discussed in the beginning, it say this voltage. So what will be the VGS? VGS will be VG. VG is what? It is R2 upon R1 plus R2 into VDD minus Vs. Now Vs is what? ID Rs. And now how can you plot this line on the transfer curve, the IDVGS curve? You can find out the x and the y intercept. To find out the x intercept, put y to 0, and to find out the y intercept, put x to 0. So let's say here, now to find out the x intercept, we have to put y to 0, that is the ID equal to 0. So what will be the VGS? VGS will be equal to this term, which is the x intercept, it is this term, and the y intercept is this VG divided by RS, which is equal to this. You have to put VGS equal to 0 and then you will get the VG by RS as the y intercept or the ID intercept. And wherever the transfer curve and the load line intersect, so that determines the operating point. Similar is the case here in the another kind of biasing network. It is slightly different here. So here this network is slightly different. How it is different? There is a feedback resistor between the drain and the gate. Like this RG, it is connected between drain and gate. So again, if we have to find out its no current is flowing, and Vg will be equal to Vd. Why? Because you can see that potential at this point and potential at this point, it will be same. VGS is equal to Vg, I can say, because source it is at ground potential, and Vg and Vd, they are at the same potential. Why? Because IGRG current drop is, it is 0. So Vg will be equal to Vd, and what will be the Vd? I can write the KVL here. It will be equal to VDD minus IDRD. Okay, let me write it back here. It is equal to VDD minus IDRD. Okay, so this becomes the equation of the load line. Vg is equal to this. Now if we have to plot this line on the transfer curve, what will be this? We can find out the x and the y intercept. What will be the x intercept here? X intercept will be this, VDD. If we put y equal to 0, so x intercept will be VDD. And what will be the y intercept? Y intercept can be determined if we put VGS equal to 0. That VGS is equal to 0. So what will be the ID? It will be the VDD by RD. Okay, it is VDD which is directly coming from here, and VDD by RD, which is the division you are getting from here. This is the equation of the load line, and intersection it occurs here. So this intersection point, it determines the operating point. So now let's see these two examples to find out the operating point in the enhancement MOSFETs. So if this is the voltage divider network, so let's try to find out the VGS. VGS is equal to VG. What is VG? VG is the voltage divider of 40 volt on 18 mega ohm. So 18 divided by 18 plus 22 into 40, that is your VG. Now what is VS? VS is 0.82 kilo ohm. So 0.82 ID. So that is the equation of your load line. Now, since we know that the current equations are different in the depletion and the enhancement mode, so now the Shockley equation is no longer useful. So we have to VGS minus VT whole square. So this equation of the current, that is mainly the saturation current equation for the enhancement MOSFET, this I am using. So we have to solve the equation number 1 and 2 together. Again, this will be in the form of a quadratic equation. So let's try to solve. So what is K here? If we look closely, some information is given to us here. So this says that its threshold voltage is 5 volt. Threshold voltage is 5 volt and ID is equal to 3 milliampere when VGS is 10 volt. So right now this value of K is not given. So with the help of this given information, we can try to determine the value of K. So let's use this information. say ID is 3 milliampere. ID is 3 milliampere and K is unknown. VGS is 10 volt and VT is 5 volt. So if we notice from here that we can determine the value of K from here, which comes out to be 3 by 25. So I'm writing it here. K we have determined as 3 by 25 milliampere per volt square. Okay, so this value of K we will be using again. So let's rub this. Now let's, using this value of K, let's try to find out the value of ID. So ID is equal to K VGS minus VT. Now what is VGS? VGS we have determined from here, that is 18 divided by 40 into 40. I am writing directly as 18 here. 18 minus 0.82 ID minus VT. How much is VT? VT is 5 volt. Well, this value of K we know, already know, 3 by 25. Okay. So if you use this K here and open this, so this will become ID is equal to 3 by 25 into 18 minus 5, that is 13, minus 0.82 ID square. Okay, if you will open the bracket and simplify, this will again become a quadratic equation. Okay, so quadratic equation, I have solved this advanced. So in advanced, I will write directly the roots. Roots which I have found by solving this equations is that 37 37.53 and 6.7. So these are the two roots by the obtained by the getting the solution of this. Now which value to select? Again we can take the help of the transfer curve and the load line. What was the equation of the load line? Load line was R18. Okay, this is written over here. This is the load line. So the transfer curve of the enhancement MOSFET, it is also different than that of the depletion MOSFET. So how will this look like? Okay, so up to VT volt there is no current, and after VT it rises in the quadratic form. So this is VT. This point here is the VT point. This point is the VT point. And now let's write down the equation of the load line. VT point is, it is 5 volt, and the load line, if we have to draw here, it is, we have to draw this equation. So 18 minus 0.82. So where is 18? If you, this, let's say 18 is here. Let's say if this is the 18 point and 18 by 0.82. Let me also calculate how much is that. 18 divided by 0.82. That is roughly 22 milliampere. So let's say this is here 22 milliampere. So the equation this will be something like this. So the intersection occurs here. Okay. So this we can say that this is definitely not 37. This value is not possible. So the possible solution is 6.7. Possible value is 6.7. So this is how we have determined the value of ID, and if we have to determine the VGS, we can use the equation of the load line to get the value of VGS. In this way we can determine the operating point of an enhancement MOSFET. Let's solve another example for getting more clarity. So let's again write down the equation of the load line. No current flows from the RC. VD. Now what is VD? VD is 12 minus 2 ID. You can notice that I'm not writing any kilo and milli here. If you will write kilo and milli everywhere, so solving the equation it will become tedious. So that's why it is advisable not to use any kilo and milli while solving these equations. And whatever the value you are getting after the solution, let's say if you are solving ID and if you are getting a particular value, let's say 5, so automatically just add milliampere after that. Okay, if you will use kilo and milli in your calculation, then getting the values of root it can be tedious. So that's why it is advisable not to use kilo and milli. So we were here that VD was equal to VG, and the VGS equation was 12 minus 2ID. That is the equation of our load line. And K, what is the device current equation? ID is equal to K VGS minus VT. Here is what? Okay, it says in this that ID is 6 milliampere when VGS is 8 volt. So we can determine the K value from here. K value will be like 6 is equal to K VGS minus VT. How much is VGS? VGS is 8 volt and VT is 3 volt. So how much is K? K is 6 by 25 milliampere per volt square. I am writing separately it here. 6 by 25. Okay, and now write down the original current equation. That is ID is equal to K VGS. VGS is how much? 12 minus 2ID minus VT. VT is how much? 3 volt. So this becomes 25 ID. I am using the value of K. 6, 12 minus not 12. It is 9 minus 2 ID. Okay, again if you open the brackets and rearrange, it will become a proper quadratic equation. You can get the value of
Okay, Bharti, you can take 5 minutes break if you need.
Okay, after this example we'll take break.
Okay.
So again you can get its root. I'm writing down the values of root. I hope all of you can also obtain the proper current equation and the roots from that equation. So the roots which I have got are 7.24 and 2.80. Okay, so these are the two possible values. Now, which of the values to pick? We have to take the help of the transfer curve. Up to Vt volt it is 0, and after that it increases in a quadratic fashion. So this is how much? This is 3 volt. And where is the equation of the load line? That is 12 minus 2 id. So what are the 2 points on x and the y axis respectively? On the x axis it is 12, and on the id axis it will be 6. So this will be the equation of the load line, and the intersection, it occurs here. Okay, and now you can easily see that the value of current, the operating point, it has to be between 0 and 6. So 7.25 has to be neglected, and 2.80, that becomes the solution. So the solution of this circuit is id is equal to 2.8 milliampere. 2.8 milliampere, and VGS will become, you can get the value of VGS from this equation of the load line. By putting the value of ID, you can calculate the VGS. So in this way, we can solve all the enhancement and the depletion based MOSFET for their biasing solution. Like whatever be the biasing network given, we have to follow the same approach. Like we have to write down the equation of the load line, and then we have to write down the current equation of the device, whether it is depletion or the enhancement. We have to write the appropriate current equation, and then solve the load line and the current equation of the device simultaneously, then get the roots, and then select the appropriate root on the basis of the position of the intersection point. So I hope that is clear. So I am also open for the doubt, and we will also take maybe a 5 minutes break.
can we start it now, sir? Dr. Bharti, can we start? Hello.
Yes, madam, we can start.
Oh, okay, sir. Please go ahead.
Okay. So in the previous half, we have discussed about the biasing in the MOSFET configuration. We have seen like different configuration like voltage divider, fixed bias, self bias, common gate, and we have taken the separate cases for enhancement as well as depletion MOSFET. And we have seen that the biasing it varies because of several reasons. The first one being like since the current equations are different in the enhancement and the depletion MOSFETs, so the biasing varies accordingly. Now we will discuss like which region of the operation should be selected for the MOSFET amplifiers. Though we have used the saturation current equation for in the case of enhancement MOSFET, but why only saturation? Why not linear? So the to know the reason, let's discuss. So let's say we have the simple most biasing arrangement shown in this circuit, this one. So we this RD is connected to drain and the VDD and so on, and the input is applied here at the gate, and the output is taken from the drain. So here, what is input? Vin is equal to VGS, right? And what is V out? V out is equal to VDS. Input voltage is the VGS and the output voltage is VDS. Now, what is the equation of this output voltage? V out. V out is equal to VDS, and if I use the KVL, so what will be the VDS? VDS is equal to VDD minus IT RD, right? V out is equal to VDD minus IDRD. Now we will try to plot a transfer curve. Transfer curve, that is the between the V out and the V in. Like if we are varying the V in from say 0 voltage to say VDD, then how will the output change? So let's begin. If V input is 0, if V input is 0, then what is the state of this MOSFET? We are for the time being we are considering the enhancement MOSFET. So if Vin is 0, so at that point the enhancement MOSFET that will be in its cutoff state. And since this is in cutoff, so drain current will be 0. And if the drain current is 0, so what will be the V out? Using this equation, the V out will be equal to your VDD because ID is 0. if ID is equal to 0, then V out will be equal to VDD. Right? So you can see that at 0 point of VGS, the value of V out or VDS is VDD. And the value of V out, it will remain VDD till the input is less than the threshold, because we know that the current in the enhancement MOSFET is 0 below the threshold voltage. So if VT is the threshold voltage here, if VT is the threshold voltage, then between 0 and VT, the drain current will be 0. So your V out will be equal to VDD. So this can be observed here. Like between 0 to VT, the output is equal to VDD. Okay. When the input is increased beyond the threshold voltage, then the drain current starts increasing, because we know this transfer curve. In transfer curve, we know that up to VT it is 0, and beyond VT it is increasing. So if the drain current increases, so what happens to V out? You can follow this. V out is equal to VDD minus IDRD. If the drain current is increasing, your V out will start to decrease. You can see like this particular region, like from A to B. Like from this A point to B point. V out is decreasing because ID is increasing, and further it will keep on decreasing. Now let's try to identify that what are the states of the transistor during these phases of the transfer curve. Between 0 to A, between 0 to VT, this is cutoff. We know the reason, because transistor doesn't operate below the threshold voltage. It will remain in cutoff, drain current will be 0, and V out will be equal to VDD. After that, the V input or VGS, it will be small. Okay, VGS is small, but VDS is still large. Why large? Because it is close to VDD, and we know that you might have been taught about the conditions for the enhancement MOSFET to remain in linear or saturation. For the linear, what is the equation? For the linear, VDS should be less than VGS minus VT, right? And this is for linear. For saturation, VDS should be greater than VGS minus VT. Okay, so now which of these two equations are satisfied over here? In region A to B, it is saturation. Why saturation? Because you can see that VDS or the V output, it is greater than the input minus VT. VGS is your input. It is greater than input minus VT. So this region, that is from A to B, that will be your saturation region. And from B to C is the region where it is greater than its output voltage. So this region, in the region B to C, it is linear. This is satisfied. Like VDS is less than VGS minus VT. So 0 to A it is cutoff, A to B it is saturation, B to C it is linear. Now let's come to the gain side. Now how do you define the gain? that is your dV out upon dV in. Okay, so that is your gain. Now if you notice this transfer curve, what is the value of this dV out upon dV in this area? That is 0. In this area A to B, region A to B, it is high because it is very steep here, and again in B to C it is low. Okay, so which of the region then should we select for amplification? It is this saturation, that is region A to B, because here slope of the transfer characteristics, that is dV out by dV in, that is quite high, and this region then should be selected for the amplifier purpose. Now to understand the amplification, we also need to know the concept of transconductance. Now what is the meaning of transconductance? Transconductance can be defined as the slope of the transfer curve at any operating point. Let's say this particular graph, this shows the transfer curve, that is ID versus VGS. ID versus VGS, that is from 0 to VT, it is 0, and from VT it is this particular characteristics, that is the transfer characteristics. And let's say if this is the operating point, okay, as we have determined in the previous half, okay, let's say this, if Q is the operating point, then the slope of your transfer curve, that is dID upon dVGS, that is your GM. Transconductance, it is denoted by GM. So dID by dVGS, that becomes your GM at the operating point. And the expression for the transconductance are also different for the depletion MOSFETs and the enhancement MOSFET. Reason? Because their current equations are different. For the depletion MOSFETs, we use the Shockley's equation. So how can we get the expression of GM from the for the depletion MOSFETs? We have to differentiate this Shockley's equation with respect to VGS, both sides. So if you do so, you will get this. The GM is equal to twice of IDSS by mod Vp, 1 minus VGS by Vp. And then for enhancement MOSFETs, it is ID is equal to this equation we use, that is the saturation current equation we use. So using this equation, if we differentiate this with respect to VGS both sides, so we get this expression of GM, that is twice of ID upon VGS minus VT. Okay, another expression can be simply obtained by simple resubstitution, that is this 2kn root of 2kn W by L into ID. So these are the two cases for the transconductance for depletion and the enhancement modes. So these concept of transconductance, it will be quite useful to determine the gain of the MOSFET based amplifiers. So now let's come to the small signal model for the MOSFETs. Now we have the MOSFETs. Let's say, let me draw the symbol, then it will be easier to understand. Let's say I have this depletion MOSFET. So this is my drain, this is source, this is gate. So how to draw its small signal model? So let's say if source is my common terminal, that is source. So, and gate is another terminal, the input terminal, and the drain is the, let's say, the output terminal. Between gate and source, what do I have? What kind of resistance may I have? Because VGS is generally in the gate side. We have the input side, we have the oxide layer. So its impedance is quite large. So in practical, so there is nothing in the gate and source, it remains open circuit. The reason being we have a oxide layer between gate and source, or the input side, which offers very quite high input impedance. So that's why gate to source it is open circuit. Now how the drain and source, what current flows between drain and source? It is the drain current. And how is that related with the input voltage? It is GM-VGS. GM-VGS. And what is the direction? Say drain to source. Now how ID is GM-VGS? This you can get from here. See, what was the expression we had used to define the GM? GM was slope of ID versus VGS, or dID by dVGS, that was equal to GM. So what is ID from here? Roughly that is GM VGS. So the same expression we are using here, ID, that is the drain dependent current flowing from drain to source, it is equal to GM VGS. And now what is this VGS? VGS is this potential difference between gate and source. Okay, between gate and source, this potential difference is VGS, so GM VGS. And do we have any resistance between drain and source? Yes, we have that resistance, that is your RD. What is RD? To get the value of RD, we have to go to the output characteristics of this MOSFET. So if we take the slope of these output characteristics, that is dID by dVGS, dID by dVGS, so it defines the slope, and the slope is the inverse of this output resistance of the amplifier. Okay, so this becomes the small signal model for the amplifiers, MOSFET based amplifiers. After studying the small signal model, we should also know like what are some of the important rules for the AC analysis. So few rules that we should have in our mind before we do the AC analysis is that the capacitors, wherever those are present, we need to replace the capacitor with the short circuit equivalent. And whereas all the DC sources, DC power sources or DC power supplies, they should be put to ground. So what we had done in the DC analysis? In the DC analysis, the capacitors they will replace with open circuit, because capacitors they block the DC, and whereas they pass the AC. So that's why AC, in the AC analysis, capacitors need to be replaced with short circuit and all the DC sources should be put to ground. So let's now come to the example of the fixed bias configuration. Let's try to draw the small signal equivalent for this particular configuration. So we have already done the DC analysis for this particular circuit in our previous discussion. So today now we are going to do the AC analysis also. So for that I need to first of all draw the AC equivalent or small signal equivalent of this depletion MOSFET. So what was that? It was gate, source and The in output side was GMVGS. It is RD. It is GMVGS, and this is RD. Now let's apply the rule of AC analysis. We are drawing the small signal equivalent or the AC analysis for this particular circuit. So I've already drawn the small signal equivalent for this MOSFET. So that is this. Okay. Now let's connect the external circuit components also. The capacitors are replaced with short circuit. Okay. And okay. So this VGG source, what? It will be put to ground. This will be put to 0. So RG is connected between what? The gate and the ground. We have put the VGG equal to 0 because, for the rule of the AC analysis that all the DC should be 0. So VGG becomes 0. So RG remains connected between the gate terminal and the ground terminal. So where is the gate terminal? Gate is here. So this is my RG. Okay. And ground. Where is the ground? Source terminal. It is at ground. You can see in the circuit the source, it is at ground. So source terminal, it is at ground. Next it is, okay, next what about RD? RD is connected between drain and the VDD. But as per the rule of the AC analysis, the VDD should be put to ground. So RD is connected between drain and ground. So this terminal is the drain terminal. So RD is connected between drain terminal and the ground terminal. RD is this between drain and ground. Now let's try to find out. Okay, so there are three important parameters that we generally determine in the AC analysis. First one is your input impedance. Second one is the output impedance. Third one is the your AC gain. So let's try to find out each of the parameters one by one. The ZI. What is ZI? ZI is the ratio of VI to II. Okay, what is VI here? It is the input current II. VI is this input voltage, that is VI. V naught is the output voltage, that is plus minus, and I naught is the direction of output current. Okay, so ZI by definition is the ratio of input voltage to input current. So if you see this in the input side, so what will be the ratio of VI and II? VI will be equal to II into RG. So this I can simply write as RG. Okay, ZI will be equal to RG. What will be the Z naught? Z naught definition is slightly different. Z naught is the ratio of V naught and I naught at 0 volt of VI. Means to determine the output impedance, what you need to do? You need to take out the ratio of V naught and I naught by putting the input voltage to 0. If you follow this definition in this circuit, what will you get? II is put to VI put to 0. It means what? The RG is removed from the circuit because we have shorted that out, and VGS becomes 0. when Vi is 0, because in this particular circuit Vi is equal to VGS, and when Vi is put to 0, VGS also becomes 0. And what happens to then this dependent current source? The drain current, that is 0. Okay, so what is left in the circuit? The components which are left in the circuits are RD and small rd and capital RD. So what will be the Z naught? Z naught in this case, it will become RD parallel small rd. Okay, so this we have to remember, that how to determine the output impedance. To determine the output impedance, we have to put Vi equal to 0. And when Vi is put to 0, VGS is also becomes 0. And when VGS is 0, then this dependent current source, it is also vanished, because VGS is 0. So this is vanished. So what is left in the network? It is the parallel combination of small rd and capital RD. And the next parameter to determine is the gain. Gain is what? We have to take the ratio of V0 and Vi. Let me rub some of the parameters which are not needed. Yes. So AV. So for to find out AV, let's write down the expression of voltage, output voltage. So what will be that? If you notice how the current is flowing, this GM VGS current is getting divided into small rd and capital RD, and this is flowing from these two resistance. This total current is GM VGS. So we can write down the current equation as, or the output voltage expression as, GM VGS, that is the current, times RD small rd parallel capital RD. Okay, with a minus sign. Why minus sign? You can notice the conventions. Like V0, the polarity assumed is plus and minus, like plus on the top, minus at the bottom. Whereas the VGS is flowing VGS is flowing in the opposite direction. GM VGS current is flowing in the opposite direction. Like this should be higher, this should be lower. All of us know that current flows from the location of higher potential to lower potential. So as per this, it should be plus should be on this side, higher potential should be at the bottom, and the lower potential should be at the top. So that's why to take this into account, we have put the negative sign, like GM VGS minus GM VGS RD parallel RT. Now what is Vi in the circuit? If you notice, Vi is equal to what? It is VGS itself. Okay, if you do so, then take the ratio, divide both sides. So what will you get? You will get gain as minus GM RD parallel capital RD. So this becomes the gain. So we have determined three important parameters here, like what? The Zi, the input impedance, Z0, the output impedance, and the gain. Let's come to the next configuration, that is self-biased configuration. Again, to find out, we have to again find out these three parameters only in the AC analysis, that is Zi, Z0, and AB. So we'll try to draw the AC equivalent for this network. So first of all, let's draw the small signal equivalent of the MOSFET. The gate side, okay, let's say this is gate, source, the RD, okay, and the GMVGs, okay, GMVGs, okay, this is the source. Now let's have a look at the network. Here we have an RS also, since this is the self-bias configuration. So we also have the RS here at the connected at the source terminal. But notice that we have a capacitor here, which is also which is bypassing this RS. So during the AC analysis, what was the rule? Rule was to short circuit this CS, because capacitor needs to be replaced by the short circuit. So that's why source will be directly connected to ground. So here source is directly connected to ground, and the RS, it will be eliminated. It will be bypassed. So that's why this RS, it doesn't appear in the picture here, because it is bypassed or eliminated because of this bypass capacitor CS. Okay, and what about RG? RG is connected between gate and ground. Where is gate? Gate is here, and the ground, it is at source. Okay, so this is RG. And what about RD? RD is connected between drain and the VDD. As per the rule, VDD should be put to ground. So RD is connected between drain and the ground. So this was the drain terminal. So RD is connected between drain and ground. Okay. So this capacitor is also short circuited. So it will be VI. We have VI over here, and this will be II, the input current. Polarity will be this. And this side C2 will also be short circuited. It will be the V0 plus minus, and this will be the output current I0. So if we notice that this network, what we have drawn here, it is quite similar to what we had drawn here. Okay, so that's why the expression for this self bias configuration, it will be quite similar. Like ZI, it will be the ratio of VI and II, that we can directly write, or we can observe that this will be equal to RG. Z0, Z0 will be equal to what? RD parallel capital RD, whereas this AV, it will be equal to minus GM RD parallel capital RD. Okay, so expression for this is quite similar, though the biasing arrangement are different. Here the biasing arrangements are different, which will give you like the different location of the operating point. But as far as AC analysis is concerned, it is similar. The self bias and the fixed bias is similar, only for the case where the RS is bypassed. Now let's move to the another next configuration, that is self bias, but where this RS is not bypassed. So this I will prefer that we will do in the next class. Let's take some other configuration, that is this one. I guess we can directly go for this one. So the remaining ones I will cover in the next particular lecture. So let's before we conclude, let's solve this particular example. So this is the numerical example. So here what we have to do, we have to determine the Zi, Z0 and AB. If we solve this example, we are also covering the voltage divider bias. So let's begin. So it says, okay, so we can start by drawing the AC equivalent for this particular network. So let's draw the small signal equivalent for the MOSFET first, that is the drain and the source. Between gate and source, we don't have anything, the high impedance open circuit. Between drain and source, this is your GMVGS. This is your RD. Okay, so this is the small signal equivalent for the MOSFET. Now let's analyze the outer biasing arrangement. Now we have this R1 and R2 connected to the gate terminal. R2 is connected between gate and ground. Where is the ground for the network? Ground, we can also observe that RS is bypassed by the capacitor. So during the AC analysis, this capacitor will be short circuited and source will be directly connected to ground. So where is the source? Where is the ground? Ground, it is at the source terminal, and this RS, it will be eliminated once again. Because of this bypass capacitor, it will be eliminated and source remains at the ground. So R2 is connected in the input side, it is connected between gate and the ground. It is R2, right? And R1. R1, where is R1 connected? R1 is connected between gate and the 18 volt. But due to the rules of the AC analysis, this 18 volt, it should be put to ground. So R1 is also connected between gate and the ground. This is R1. R1 is connected also between gate and the ground. And the input side we have VI and II. Okay, and the output side, what we have, the RD. RD is connected between drain and the 18 volt, or in the terms of AC analysis, it is connected between drain and the ground. So it is drain and the ground. And again V0, it will be the V0 plus and minus, and the output. Okay, so what is Zi? We have determined Zi will be the ratio of Vi and Ii. Okay, Zi is the ratio of Vi and Ia. So what will be that? If you notice here, this the II current itself is divided in R1 and R2. So effectively we can write the Vi and II ratio of these as R1 parallel R2. What is this? Parallel combination of 110 mega ohm and 10 mega ohm, which will be less than 10 mega ohm. So that is the Zi. Z0. What is Z0? Z0 you can see from here. It is small rd parallel capital RD. How? What was the definition? Definition was that Z naught was the ratio of V naught and I naught at 0 volt of Vi. When Vi will be 0, VGS will be 0, and GM VGS source, it will be eliminated. So what is left in the network? That will be the parallel equivalent of RD and capital RD. So it will be small RD is how much? We have some information here about the device that GOS is 10 micro Siemens. So it is 10. So this is your small RD parallel capital RD. Capital RD is 1.8K. Okay, so it is quite near to 1.8K itself. Then AV. So what will be the AV here? So I guess it will be better if we can write down the AV expression. The AV expression, let me rub this. To determine AV, we can write down the V naught expression first. What is V naught? V naught is minus GM VGS, that is the current, times small rd parallel capital RD. Okay, this is the V naught expression. And what is Vi? Vi here you can see Vi is equal to VGS only. Vi is what? The same potential as that of this point and this point. Okay, so Vi is equal to VGS. Okay, so when you will take the ratio of V naught and Vi, it will again be the same as minus GM small rd parallel capital RD. Okay, but here small rd and capital RD are known. Small rd is this, the inverse of 10 microsiemens, and capital RD is 1.8 kilo. But what about GM? How will you determine GM? GM has to be determined by the DC analysis. So this is here the importance of DC analysis comes. In the case of BJT, also like whenever we are doing the AC analysis, there in the expression of the whether the voltage gain or the input or the output impedance, we get the expression of we get the what incorporation of small re, that is the small signal equivalent, that small re. And how can we determine the small re? Small re can be determined by doing the DC analysis. So similarly here the GM has to be determined by the DC analysis. So how can we determine the GM? Again we have to follow the same procedure that we have learnt in the beginning, that we have to first of all find the operating point like ID and VGS. We have to find out the ID and VGS to determine the operating point, and then GM is given by the ratio of twice of ID upon VGS. Okay, sorry, I am writing this for the enhancement, but actually this is depletion MOSFET. So what we have to use the different formula, that is the Shockley's equation based formula. So what was that? GM was equal to twice of IDSS by mod of VP into 1 minus VGS by VP. This was the expression. If I go back, you can see transconductance. Yes, we are using this particular transconductance expression. Twice of IDSS mod Vp into 1 minus VGS by Vp. In order to calculate GM, again, all the quantities are known. IDSS is known, Vp is known. Only thing not known here is your VGS. VGSQ, that is the operating point VGS. So how will you find out the operating point VGS? Again, by doing the DC analysis. Again, what is the procedure? Procedure is the same. We will use the the Shockley's equation, current equation of the depletion MOSFET, and we'll write the load line equation. And then we'll solve both of these equations parallelly. One quadratic equation will be formed, root will be calculated, and appropriate root will be chosen. And using the appropriate root, we can find out this VGS, operating point VGS, and then GM will also be determined, and then we have to put that GM, calculated GM, in this expression to ultimately get the value of gain. So this is how the AC analysis is done, and in the AC analysis itself, whatever the parameters are determined, to calculate those parameters, we have to do the DC analysis. That's why both of the analysis, the DC and the AC analysis, they go on and on, like hands on and on. So I guess we can stop here today, and we'll continue with the remaining parts, that is the AC analysis of the enhancement MOSFETs, and few design examples will cover in tomorrow's class. Dr. Meenka.
Yes, dear participants, if there is any question so far, you may ask. Otherwise, let us conclude the session for the day. Do we have any questions so far? Please type N in the chat box if you don't have any questions so far. And let us conclude the session for the day. I hope you can hear me. Please type N in the chat box if you don't have any questions. Okay. Okay, so thank you so much, Dr. Deepak Bharti, for enlightening lecture you have taken for depletion type and MOSFET, the analysis related to this, how the AC signals can impact, and how the DC analysis can be impacting the results. All these analysis has been covered by Dr. Deepak Bharti. So tomorrow, whatever is left over, we will be discussing, Dr. Bharti will be discussing at 10 a.m. in the morning. We are uploading that quiz very soon, and you have the session starting tomorrow at 10 a.m. 10 a.m. to 11 a.m. Dr.